Okay, hello everyone. Good afternoon. Can you hear me now?
Yes, sir.
So I have started recording. Can you check if it is recording?
Yes, sir. It started.
Okay. So we have started a new topic called decidability, right? In decidability में हमने बहुत सारे theorems देखे थे. So we looked at decidable languages.
रात में क्या बनाएंगी तो गए हुई मैम जो आपकी मर्जी बना लो
Okay. So we looked at several decidable languages. For example, we looked at ADFA. It's a decidable language. Then we also looked at ANFA. So A is for acceptance. Sub DFA, sub NFA is the language of decidability of the deterministic finite automata, non-deterministic finite automata. We also looked at AREX, which is the language of decidability of regular expressions. Then we looked at EQ, EDFA, that is the emptiness of DFA. And then we looked at EQDFA, if two DFAs are equivalent or not. And we looked at the symmetric difference and we talked about it, right? So this was all about regular languages. So today we will see some decidable problems in decidable languages for context-free languages. Context-free languages. Okay. So the first problem that we will look at is called ACFG. ACFG is a problem that we define as that given some grammar W and some grammar G and a string W, G is a grammar, is a CFG that generates W. Okay. So what do you think about this language? Is it decidable? If it is, then how and why? So first of all, let's try to understand what does it even mean by this language A sub CFG. Can anyone answer?
Sir, it produces is a set where all the CFGs G produce a Turing machine W.
No. So this set A is a collection of all context-free grammars, all context-free grammars, all possible context-free grammars, small, big, very large, every context-free grammar that you can think of. So this set contains a pair of a grammar and a string that this grammar generates. Now imagine a grammar, a small grammar, a very simple grammar, a simple context-free grammar. We know that even a simple context-free grammar can generate an infinitely large collection of strings, right? So it means that suppose I have a grammar. So let me write a simple grammar here. S is the starting symbol, and I say that S is, let's say, A, S, B, or empty. Okay, so we have just two rules, and those rules are that I can start my derivation with the starting symbol S, and then I can have replace this S with ASB, and I can keep doing it as long as I want, and then when I have to finish, I can just stop it with empty. So what are the strings? For example, if I say this is my grammar G, then what are the strings in my grammar G? What are the strings in my language G? It definitely contains
Empty.
empty. It contains
Then AB.
it contains AABB, it contains AABBB, and so on and so forth, right? So the property of the strings of this language is that they are in a form that we have equal number of A's and equal number of B's. And this number n could be anything, right? So we can write it as it contains all strings of the form AN, BN, where n is greater than equal to 0, right? So, so this is a very simple CFG, and we know that this is a context-free language because we cannot construct a DFA. Now, for every possible string that we have here, so this, and every other string that we have, there are infinitely many strings. We can make a pair of this grammar G with the string. So this is one pair. The other pair could be this G with AB. The other pair could be G with AABB, and so on and so forth. So there are infinitely many pairs which will be inside this set ACFG. And for every possible grammar G, this set of infinitely many different pairs will be part of it, right? So the question is this set decidable or not? So when we say that a set is decidable or not, it means that can we decide the membership query for this set with a decidable Turing machine or not? If we can do it, it means the set is decidable. If we cannot, then the set is not decidable. So with this, we say that, so we can write a theorem. The theorem can have two possible ways. We can say that ACFG is a decidable language. Okay, ACFG is a decidable language. So how to prove that this is a decidable language? So it means that we want a machine M, that whenever this is given a string G, a grammar G and a string W, it tells me yes or it tells me no. So when it tells me yes, it means that G generates W, and when it says no, it says G does not generate W, right? Can we do that? How would we do that? How to prove this theorem?
Sir, won't we need to know pushdown automata for this?
No. Why do we need pushdown automata?
I'd assume since we're making a machine, we probably need the machine for CFG.
We have Turing machine. Turing machine is more powerful. So yeah, if we have a Turing machine, it's okay.
Okay.
Okay. Okay, so the proof is very simple. The proof says that, so on the input, so what we will input to this machine. So remember, this is the machine M. So this input is, this pair is the input, okay? And this yes or no is the output, right? So we say that on the input G and W, where G is a CFG and W is a string, what we need to do? We need to do these three things. Convert G. Okay. So first of all, G is given as an encoding. Of course, we cannot write the grammar as is on the Turing machine state. So we need to convert the grammar in some encoding, and that encoding must appear on the tape of the Turing machine. So this input is encoded. So we need to first decode. So we say that convert G to an equivalent grammar, and then equivalent grammar in Chomsky normal form. In Chomsky normal form. Why do we need Chomsky normal form? Because we need to have some bounds on it. And if you remember the Chomsky normal form, we knew that we can convert any CFG into Chomsky normal form. And there are some properties as well, right? So if I have some grammar in Chomsky normal form, then what we would do? We would say that list all derivations with 2n minus 1 steps. Okay, where n is the length of W. Okay, except if n equal to 0, then instead list all derivations with 1 step. Okay. Number 3, if any of these derivations generate W, except, okay, otherwise reject. Okay, so what we would do, so first of all, we know that G is input to the machine as an encoding. So this encoding has to be converted and it has to be decoded. And once we have the grammar, we have some understanding of the grammar. What we would do, we would create an equivalent Chomsky normal form of that grammar. And we know that we can do it because there's an algorithm. We studied that algorithm, how to convert any grammar into Chomsky normal form. Once we have the grammar inside the Chomsky normal form, now we know that Chomsky normal form allows us to drive strings in some systematic algorithmic way. So what we would do, we would say, okay, what is this W? So what is the length of this W? Let's say n is the length of this W. Then what we would do, we would try to generate, we will try to drive all possible strings of the length in 2n minus 1 steps, where n is the number of the characters in the string W, or the length of this string. So if W can be generated by grammar, then it must appear in one of those derivations. Okay. If it cannot be generated, it will not appear in those derivations. So if it appears in one of all those possible derivations, accept it. If no, then reject it. Since we are able to answer both questions yes and no, it means that this Turing machine M, so this is the M Turing machine M, right? This Turing machine M is a decider because it answers both kind of questions of the form yes and no. Therefore, this is decidable. That is the end of the proof. Is this in clear?
Sir, can you repeat it?
Repeat what?
Can you repeat how the part 3? The third part?
So do you remember Chomsky normal form?
Yes.
Okay. So what we would do, we would convert this grammar G into the equivalent Chomsky normal form. And once we have the grammar in the Chomsky normal form, we know that the Chomsky normal form has some format. And what we would do, we would say that, okay, starting from the starting symbol, चूंकि हर grammar के अंदर एक starting symbol होता है, so we will pick that starting symbol and we will say कि इस starting symbol से हम क्या-क्या चीजें generate कर सकते हैं, ठीक है?
So
हम क्या-क्या चीजें generate कर सकते हैं, तो it can go up to infinite, but we don't have to go up to infinite. What we need to do is we only have to go up till 2n minus 1 steps. एक step, 2 steps, 3 steps, 4 steps, 5 steps, till 2n minus 1 steps. What is n over here? N is the length of the string W. अगर string की length W की length 1 है तो 2n minus 1 which is 1. अगर length 2 है तो 2 times 2 minus 1 is 3 and so on and so forth, right? So we will go up to that number of steps. Okay. And we can guarantee because of the structure of the Chomsky normal form that if the W is a string that can be generated by the grammar, then it must be one of those 2n minus 1 possible. It could be one of those strings which can be generated in any 2n minus 1 steps, right? Not 2n minus 1 steps, but any of those things. So let's say the starting symbol S था, ठीक है, this is the end of the proof, okay? Starting symbol S था, हम S से जो है वो किसी intermediate form में गए, फिर S से हम किसी और intermediate form में गए, फिर किसी और intermediate form में गए, and so on and so forth. So this is one step. So from here it's one step. From here it is second step. It is third step, and so on and so forth. So we have to do it till 2n minus 1 steps. Okay. Acha, this is not just one possible output, because we know that this is basically a tree. So S can give us many different things, right? And we can keep creating such strings. So this is the leaf, for example. So there might be any leaf. The only restriction is that the length of this path should be less than equal to 2n minus 1. Okay. So this
Yes.
makes sure the number of steps. तो जब हमारे पास सारी लीफ आ जाएंगे तो we will just verify if this is W, if this is W, if this is W, if this is W, and so on and so forth. If one of them is W, we accept. Since there are only polynomial number of things, there are only finite number of things that we have to check, and not just finite, polynomial number of things. Sorry, polynomial. Okay, there are only finite number of things, so we can check all of them, right? If one of them
Yes.
is W, fine. If none of them is W, we would say no. If one of them is W, we say yes. Otherwise, we say no. And since we are able to answer both yes and no, it means that this is decidable. This M must be a decidable machine. It's a decider. Is this in clear?
Yes, sir. Thank you.
Any other question? Okay, this is very important problem actually. This is really very important problem. For example, this problem actually is the compiler problem. Okay. For example, जब हम किसी language के अंदर program लिखते हैं, let's say I have a program test.c++. तो test.c++ एक program है जो मैंने C++ language के अंदर लिखा है. I will pass this program to my compiler, right? And compiler will check if the program written over here is in the language of C++, proper language of C++, right? So actually I'm creating, so this compiler is basically a Turing machine, which checks whether this program is written in the right language or not, right? So this program test.cpp is an instance of W. So what is this compiler doing? This compiler has a grammar G for C++, and this test.cpp. This test.cpp is basically W, right? So this compiler is checking whether this W can be generated by the grammar G of the C++, right? And if it can be generated, it means it's okay, and it will say fine. If it cannot be generated, it means there is some problem and there is syntax error. Okay, so this is a valid question. It's not a hypothetical theoretical question. It's a valid question that we come across when we are designing compilers. So compiler does much more than this. It does not only check whether this can be generated, it actually compiles. That is, it tries to understand and it translates it into a language or a format which the machine understands, right? So it doesn't just check whether this is correct or incorrect. It checks, it does more than that, but checking is definitely one part of it. Okay. Okay. So now we have another problem which we call ECFG. ECFG is a problem that given any grammar G, encoding of a G, we check. So first of all, G is a CFG. Okay. And language of CFG G is empty. Okay. How do we prove it? Any ideas? Yes, any ideas?
Yes, sir, it's decidable.
Yes, it is decidable, of course, but how?
Can't we just check the whole tree, and if it does get a solution,
मतलब ये है कि
reject it?
there could be infinitely many strings, right? So which string to check? तो हम ये वाला theorem use कर सकते हैं, this theorem, कि ACFG is decidable language, right? And then we can say that कि we have the grammar. इस वाले problem के अंदर हमारे पास grammar है. So this is this grammar, and then we generate a string and say if this string is in this grammar or not. So how many strings should we check? Infinitely many? This is impractical, right? So we cannot do that.
No, we can convert it to the Chomsky normal form
फिर
and
क्या
then check. And because it has a finite number of steps, 2n minus 1.
हाँ, लेकिन 2n-1 steps है ना. और जब हम when we were doing the other theorem in which we had a string w, so we generated all strings which can be generated in 2n-1 steps. 2n-1 is the finite number. So it gives us a finite number of strings, and we can check those finite number of strings whether one of them is w or not. But the problem over here is that we don't have any w. We just are trying to say if the language of G is empty or not. So what does it even mean? The language of G is empty.
It
Nothing
doesn't
can
accept
be
it.
generated by this language, this grammar, right?
Yes.
So if nothing can be generated by this grammar, how did we do it in case of DFA, EDFA? Do you remember how did we do the EDFA thing?
So with the breadth first search,
हमने
we
breadth first
check
search.
all.
We have something similar going on, but not exactly. So what should we do? So let's see what is the proof. Okay. So let me write the proof and then I will try to explain. So again, we will create a Turing machine M. Okay, and for this M, we would say that on the input, okay, we will just one input, that is G, which is a CFG. What we would do? We would mark all terminal symbols in G. Okay. And we do repeat until no new variables get marked. Number 3, it's indented because it is part of the line number 2. Mark any variable A where G has a rule, that is the production rule. Each symbol U1 to UK has already been marked. Come out of the loop if the start variable is not marked. Sorry. Except reject otherwise. Okay. Do you understand this proof? So in this proof, we are going the other way. So let me explain. So I will come back to this proof. So let me explain by an example. So what happens in a grammar? So suppose I have a grammar G. ठीक है, इस grammar G के अंदर हमारे पास एक starting symbol होगा, इसके बाद हमारे पास set of variables होगा, ठीक है, set of variables के अंदर हमारे पास बहुत सारे variables हो सकते हैं. So this set of variables as B1, B2 and so on. it also contains S, right? And S is the starting symbol. So what actually happens in the grammar? So we start with the starting symbol and see that what does it drive, right? So it drives some string. Then what can we drive from this string? We can drive some other string, and so on and so forth, till we receive a string composed only of terminal symbols. Right? In this particular case, we say that this symbol, starting symbol S, drives this terminal symbol. So if I take the example of if I take the last example, we know that the starting symbol S drives A, B, 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 right? In 0 or more steps. So when I put star over here, it means that in more than in 0 or more steps. So we know that this S drives this string. That is, we can find a path starting from S all the way to this terminal, this string composed only of the terminal symbols. So over here in this proof, what we are trying to do, we are starting with the terminal and going in the other direction. We say that, okay, what are the terminal strings? What are the strings that are generated? And can we figure out that if I start with any string composed only of the terminal symbols, is it possible that I can reach back to the starting symbol or not? If I can get back to the starting symbol, it means that starting symbol will generate this terminal string. And if I cannot, it means that it's impossible to generate any string. So that's exactly what it says, that it says if the start variable is not marked, then accept, otherwise reject. You get it? Is this in clear?
Yes.
Okay. If no questions, then we can move on. Okay. Similarly, we have this thing which we call equivalence. So we have EQ, CFG. There is given two grammars G and H. Okay. Okay. G and H are CFGs. And L of G is equal to L of H. So we have a theorem. It says that EQ CFG is decidable. Okay, how can we prove?
Sir, can we do it like with sets like we did last time?
Okay. So the thing that we did with regular languages, we cannot do it over here because the set of context-free grammar, the context-free grammars are not closed under complementation or intersection. So for example, if I have a language A and I have a language B, and I say that A and B are regular, then A union B is regular, A intersection B is regular, and A complement is regular. So these are all regular. Okay, but we cannot say the same for context-free. For example, if I have A and B are context-free languages, then I cannot say A intersection B is CFL. I cannot say. Not necessary, right? Similarly, A complement is CFL, I cannot say. So the problem is that the class of context-free languages is not closed under complementation or intersection. Union, yes, but so we can say that A union B is CFL. Yes, we can say that. But is A intersection B CFL? No, we cannot say. Is A complement CFL? We cannot say. Okay. And the reason will be clear in the next chapter, which we will study, which is about something related with, I mean, we will continue with this discussion where we change the problem, okay? And we will do some other problems which are related to undecidability of the things, and then we will see, okay, why it is the case, okay, it's not possible, okay? But the problem is that, yes, the proof of this theorem
Sir,
says that EQ CFG is decidable. Okay, how does it prove it? We are just delaying it. Yes, please go ahead.
sir, uh, so we can take a union of A and B, right?
Yes.
So, sir, if we take a union of A and B
Mhm.
and then see if the output does not change, then it means that they're equal, right?
And how would you check they are not? Uh, does not.
If
That's
they're
exactly what we want to check.
sir, we'll know that they're equal.
Okay, listen. So
They're
what you are
not
saying
equal.
कि हमारे पास एक grammar है G, हमारे पास एक grammar है H. So what you would do, we would say कि let's create a new grammar X, which is the such that the language of X is the language of G, union language of H, right? This is exactly what you're saying.
Yes.
Okay. फिर हम क्या check करेंगे कि is L of X same as L of G and L of X is same as L of H, right?
Yes.
Right.
Yes.
So what you were doing, so initially we had to check L of G is equal to L of H. Now we have translated or transformed this problem in checking these two things. X भी CFG है, G भी CFG है, H भी CFG है. अगर G और H को हम चेक नहीं कर पा रहे थे तो हम X और G को कैसे चेक कर पाएंगे? You get the problem?
Yes, sir.
Okay, so yeah, so the idea is right, but I mean, idea in a sense कि हाँ exactly हम ऐसे यही करना चाह रहे हैं, लेकिन हम ये कर नहीं सकते, ठीक है? So you have to take my word कि we will come back to this thing, right? Okay, and sorry, it's not a theorem, sorry. So we say that is not decidable, okay? So is not decidable. EQ CFG is not decidable, and we will prove it that why it's not decidable later on. We cannot prove it, right? It requires some additional tools which we don't have at our disposal, so we will delay the proof. Okay. We have another theorem which we can think about it, and it says that every context free language is decidable. What does it mean? इसका मतलब क्या है? Let us try to understand what does it even mean. क्योंकि एक तरफ हमारे पास कॉन्टेक्स्ट फ्री ग्रामर्स हैं, कॉन्टेक्स्ट फ्री लैंग्वेजेस हैं, और दूसरी तरफ डिसाइडेबिलिटी है. डिसाइडेबिलिटी का मतलब है वी कैन हैव अ ट्यूरिंग मशीन. So it means that, so the proof is very simple. So what we would do, we would create a Turing machine M, okay? And this Turing machine M will receive some input W, right? So before we do that, what we would say that let G so we say that let G be some CFG. Okay. Okay. Now we can construct a Turing machine M sub G for G. And remember, G is arbitrary. When I say that G is arbitrary, it means that it doesn't matter which G I'm talking about. Any given context-free gamma G, we can do that. Now, what this TM MG would look like, what it will receive. It will receive some input W. So that is, we have this Turing machine MG, and this Turing machine will receive some input W, and it will say yes, and it will say no. For some cases, it will say yes. For some cases, it will say no. So what happens? So we have this MG, and when MG receives the input W, what it does, it runs, it creates a Turing machine S on the input GW. If this machine S accepts, then you accept, otherwise reject. And how do we know that this machine S will accept or reject? Because of the theorem, this theorem that we just did. Because of this theorem. Okay, so this Turing machine S is because of this theorem. Okay, so this is the end of the proof. Any questions? So we say that we have regular languages. Okay, then we have context-free languages. Okay, then we have decidable languages. And then we have Turing recognizable. Okay, so we have this kind of a structure that at the heart of this structure, we have regular languages. Then little bit above it is context-free, then above it is decidable, and above it we have Turing recognizable. So this also gives us a hierarchy, which is also sometimes called Chomsky hierarchy, कि हमारे पास regular languages हैं जो सबसे आसान हैं, जिनके लिए हमें सबसे आसान या simplest machine चाहिए. जैसे जैसे हम इस hierarchy में बाहर की तरफ आते हैं, तो we need more and more complicated machines. So for this kind of languages, we need DFAs, NFAs. For this, we need push-down automatas. For this, we need decidable Turing machines. And for this, we need Turing recognizers. And everything that is outside it, it's beyond our understanding of computation. So if a language is somewhere, for example, इस पूरे structure के अंदर मैं कहता हूँ कि there is a language X. I don't know where is this language. This language X could be here, or it 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 is outside. If it is within regular, I can use a Turing machine. Definitely I can use a Turing machine, but I can also use a simpler, smaller version of a machine, which is DFA. If it is context-free, I can use a Turing machine, but I can also use a simpler push-down automata. If it is a decidable, I have to use a Turing machine. If it is Turing recognizable, I have to use a Turing machine, but this Turing machine will be little bit different from the decidable because it cannot answer the no questions very easily. और एक और possibility है कि ये language X हो सकता है इस पूरे structure से बाहर हो. And if it is outside the complete structure, it means that it is impossible to think about any Turing machine or any machine for that matter, which can accept or understand or recognize or decide or do whatever with it. So the string of this X, so we cannot come up with, or we cannot even comprehend any machine which can discriminate, which can check the membership of the strings of the language X in any way. It's impossible to even think about it. Which leads us to the new topic, which we call undecidability. So we just saw one language which is undecidable. So now we will see that why it matters, or what does it even mean by undecidability. So anything that is outside this circle, anything that is outside this circle, this ellipse or this class is undecidable, right? कोई चीज यहाँ पे वो भी undecidable है, जो चीज यहाँ पे वो भी undecidable है, but जो चीज यहाँ पे वो definitely undecidable है, और जो चीज यहाँ पे that's not even Turing recognizable. Okay, any questions before we proceed? Okay, so we had seen a DFA. Okay, we have seen a CFG. Okay, what about a TN, which we defined it as MW, where M is a Turing machine so the question is a TM decidable?
Yes.
Yes or no? Okay, let's construct a Turing machine. If it is decidable, we should be able to construct a Turing machine, right? So let's try to construct a Turing machine and see that if it is possible. So let's construct a Turing machine U. Okay, and this Turing machine U is a Turing machine that that does something with this language ATM, right? So I will explain what does it do, what actually it does. So we say that on the input, so this machine will receive some input M and W because this is for the ATM. What we would do, we would say that simulate M on input W. That is, when it receives this encoded input, it takes the first part of the encoded and decodes it as N. Then it simulates the machine, Turing machine N, and then it sends this second part of the message or second part of the input as the input to the simulation, right? Then what it will do, so either this machine will decide W or it will not decide W, right? So we say that if M ever enters its accept state, then accept. Okay. If M ever enters its reject state, reject. Okay, but there's a problem. Do you see the problem?
So if it's decidable, why would you reject it?
Decider rejects, right? Sometimes it accepts, sometimes it rejects sometimes.
Yeah, but the criteria for decidability is the string should be either accepted or rejected, right?
Yes.
So the main Turing machine not the simulated one, but the main Turing machine, if it gets an input, whether it's accept or reject, the main Turing machine should accept it either way, right? If
Okay.
it gets an input, it gets an output from the simulated Turing machine.
Okay, but this is not the question. The question is, imagine we have a Turing machine. Okay, और अब ये Turing machine कुछ भी हो सकती है. ये decider भी हो सकता है और recognizer भी हो सकती है. ठीक है. So our question is, let us construct a set which we call A sub Tm, in which we pass two things, M and W, where M is the encoding of a Turing machine and W is a string. And our set checks whether this W is accepted by the Turing machine M or not, right? So maybe it's a good idea to write except here as well. Okay, so whether this Turing machine M accepts W or not. So when do we say a machine accepts a string?
So when it reaches either the accept or reject state.
ठीक है, तो हमारे पास जो ट्यूरिंग मशीन होती है वो दो तरह की होती है, एक तो डिसाइडर होती है और एक रिकग्नाइजर होती है. डिसाइडर ऑलवेज विल होल्ड, राइट? होल्ड का मतलब है स्टॉप. So when they stop, they either stop in the accept state or they stop in the reject state. And depending on where do they stop, we know कि जो input string थी वो accept हुई है कि reject हुई है, right? Right?
Yes.
Okay.
Yeah, yeah.
So let's say we have this Turing machine M. We don't know what kind of Turing machine it is. If it is a decider or a recognizer, we don't know. We have a Turing machine M and we receive an input W. So what we do, we try to simulate the Turing machine M and send this W to this M. Ab ye Turing machine M, it will start its work on the W, and after some time, it accepts W. Okay? Then we know that the U will find it out from this proof, because U is a Turing machine that is simulating M. So you will figure it out. Okay, it is observing M. As soon as the M enters into its accept state, it will accept. Now suppose W was such a string which makes M to go into reject state. So U is again watching. So you will check के M as M जो है वो reject state में गया. So as soon it goes to reject, you will reject, right? Okay, this W is not part of this machine M. But the problem is that these are not the only two things this machine M can do. It can go to accept state, it can go to reject state, and it can stay in an infinite loop kind of thing, where it doesn't go in any state. It either loops between these different states, or it's stuck on some state, or it does something which we don't know. So for you to figure out whether it is going into accept or reject is not 100% guaranteed, because you may be waiting for infinite time before it can figure it out whether M goes to accept state or reject state, or it is going into an infinite loop, right? जैसे ही M accept state पे गया, U को पता चल जाएगा, उस बता देगा मैं, ठीक है. जैसे ही M reject state पे गया, U को पता चल जाएगा and it will say reject. But if M goes into an infinite loop, there is no way you can figure it out कि ये कौन सी state में है, ठीक है, or whether it will ever go to accept state or reject state. So it's a state, or it's a condition for you where it cannot figure it out. So what we say that U is a recognizer, right? So we say that U recognizes ATM, but not decide ATM. It seems like ATM is not decidable, but this is not a proof. This is just a way to motivate that this is not possible. Okay, this machine U is very interesting machine. We call it universal Turing machine, which we will look at in more detail.
सर M जो है वो डिसाइडेबल है या नहीं है?
क्या कह रहे हो?
M डिसाइडेबल है क्या?
We don't know. We don't know. M could be anything. It could be decidable. It could be undecidable. We don't know. It's just a Turing machine.
यानी कि आपने ऊपर लिखा होता है M decides W.
Yeah.
इसका ये मतलब नहीं डिसाइडेबल हुआ.
this is the question. This should be written in a different form. M is a Turing machine that accepts. I think accepts is a correct word. It should not be decide. It should be this is correct. Sorry for that. So M is not necessarily a decider, right? M is a Turing machine that accepts W. In fact, the other way is also not, I mean, that's also not incorrect in a sense के हो सकता है M decidable हो, लेकिन for you it is not possible to check whether it is decidable or not. Because M could be anything, right? So if it is decidable, yes, it can find it is decidable. But what if M is not decidable? Then it cannot find out whether it is not decidable. So that was also correct, but it makes more sense to write except step. Is this in clear?
Yes, sir.
Any questions? कोई सवाल? Should I repeat it?
No, it's clear, sir.
Is it clear to all?
Yes, sir.
So let me quickly go through it and इसको connect करता हूँ ADFA के साथ and then we can move on to the new things. Okay. So what is ADFA? So ADFA says that we are given some B and W. Okay. And B is a DFA and W is a string. And we need to check if BW is in ADFA or not. Okay, which can be done very easily because we can always simulate the DFA from the encoding of B, send W to this simulation, और जब W पूरा run हो जाएगा इस machine पे, तो it will end either in an accepted state, यानी कि final state, or it will end in some other state. If it ends in final state, we say that W is accepted, otherwise it is not accepted. In that particular case, we will be able to answer both yes or no questions very easily. So similarly, we pose this question about ATM. There is given some M and W, where M is a TM. We don't know what kind of TM it is. It's just a TM. W is a string. You can think about it this way. Yeah, we have a machine M. It receives this W and it gives us yes. W is in the language of M. Or it says no, W is not in the language of M. And there's a third possibility that it may go into an infinite loop. We don't know. हो सकता है कि ये सिर्फ दो चीजें हों या हो सकता है कि तीनों चीजें. We don't know because if I say that M is a Turing machine, then M could be anything, right? It could be a recognizer, it could be a decider, we don't know. So the question is, if I have this set ATM, which contains all such pair M and W, where M could be any TM and W could be any string. So my question is ATM decidable? Okay. The answer to this question, which leads to a proof, is little bit involved and it requires some other things in math that we will study now. But it seems that it is not decidable. And the thing is that कि जो एक natural answer हो सकता है कि let us create, जिस तरह से हमने DFA के लिए बनाया था कि let's create a machine which simulates the DFA B. So we would do the same thing over here. Let's create a machine S or U that simulates the Turing machine M. और जब वो simulator U के पास M आ जाएगा, then it will send the W to M and check whether this M accepts W or it rejects W. If it accepts W, you will accept the input. If M rejects W, you will reject the input. But there's a possibility this M may never end. It may never go into accept state or reject state. In this particular case, we cannot do anything and the U will go into an infinite loop. So it seems like U is not a decider, rather U is a recognizer. It does not answer this question whether it is impossible to come up with a decider, but it gives us a hint that it may be very difficult even if it is possible. So we will now look at some proof. But before we go to the proof, which we will do after the Eid, because it's really involved, we have to think about a few other things. Is everything clear so far? So I will shift my attention to some discrete maths. Okay, so I will talk about sets, especially countable sets and uncountable sets. Do you know what is a countable set?
Of something we can count.
Okay, give me some example. Suppose I have a set A which contains 1, 2, 3. Is A countable? Yes or no?
Yes.
Yes, we can count the number of elements in A. So we know that there are 100 elements, so we can count. Okay. Suppose I have another set B which contains, let's say, -10, -9, all the way till 50. Is this countable?
Yes.
It is countable. Suppose I have another set C which contains like 2, 3, 5, 7, 11, 13, and 17. Is it countable?
Yes.
Okay. Okay, so let's consider another set D that contains 0 and 2 and 4 and 6 and 8. And is it countable?
No, it isn't.
It is not countable. Okay. So what is a countable set?
It is finite.
No, that's not the definition. So let me write the definition of a countable set. So we say that a set is countable if it is finite. Okay, this is the first condition. If it is finite or it has the same size as of set of natural numbers. Okay, so this set D has the same size as the set of natural numbers. Do you agree with that or not? So what is set of natural numbers? So let's consider a set of natural numbers. So my set of natural number contains 0. Okay, 0, 1, 2, 3, 4. So this is a set of natural numbers, right? 0 is there, 1, 2, 3, 4. So my set D over here is 0, 2, 4, 6, and so on. So what do you think about these two sets? Do these sets contain exactly the same number of elements or different? One may say that D contains half as many elements as N, right? Because N contains both even and odd, while D only contains even. So it means it must have half as many elements as N, right? Right or wrong?
Yes.
But that's wrong. The problem is you can construct a one-to-one correspondence between the set of natural numbers N and set D here. How? So you say that we pick any element N, okay, and multiply it by 2. we get an element D. So for example, if I say I have a function f that is defined between set of natural numbers and D, then this function can be defined as f of n is 2n. Okay, and this is an invertible function. F is an invertible function. Is it an invertible function? So I can say कि मेरे पास एक correspondence है 0 की 0 के साथ, 1 की 2 के साथ, 2 की 4 के साथ, 3 की 6 के साथ, इसी तरह से 4 की 8 के साथ होगी, and so on and so forth. For every element that you find here, you find an element here. And for every element that you find here, you find an element here. Right? So this means there is a one-to-one correspondence between the set of elements of set of natural numbers and the elements of the set D here. It means that every element that you find in N, you can find a corresponding element in D. And for every element in D, you can find a corresponding element in N. It means that the number of elements are same, which means the size of the set N is same as the size of the set D. And that exactly is the definition of a countable set. So we said that a set is countable, either it is a finite set, and if it is not a finite set, like D and N, then it must have the number of elements same as the size of the set must be same as the size of natural numbers. So set D is countable. So counterintuitive example, if N is this, let's say I have a set A, which contains 1, 3, 5, 7, 9, and so on. And I have a set B, which contains 0, 2, 4, 6, 8, and so on. And I have another set C, which contains 0, 1, 2, all of these numbers. So my claim is that size of A is same as size of B is same as size of C. So these three sets have the same sizes, because for every element in C, I can have a corresponding element in A and a corresponding element in B. For every element in A, I can have a corresponding element in B and a corresponding element in C. And the same thing goes for B. And it goes in all directions. So therefore,
Just
yes.
sir, same size होने से countable होने का क्या ताल्लुक है?
This is the definition. So we say that a set is countable if it has exactly the same size as the set of natural numbers, because we say a set of natural numbers is also countable. So this actually has two different terminology. So sometimes we call it countable. Okay. Sometimes we call it infinitely countable. Okay, so these two are interchangeable. Infinitely countable is it's very clear. Okay, we are talking about infinite sets which are countable, which has the same size as the size of natural numbers, and countable is for finite. But sometimes we use countable for both, whether it's infinite or finite, doesn't matter. So whenever we are able to count, and when we are able to count, when we know exactly the number of elements in the set, or we know that the number of elements is exactly same as the set of natural numbers. The set of natural numbers, अच्छा इसका मतलब ये है कि if I can sequence something, okay, ठीक है, अगर मैं किसी की कतार बना सकता हूँ, if I can make a sequence of something, if I can make indexing of something, और वो इंडेक्स जो है वो 1, 2, 3, 4, 5, 6 हम कर सकते हो, 0, 1, 2, 3, 4, 5, 6. And if I can do that indexing of any set, that set becomes countable by definition. Because we can count. Now we know how many elements are there. Even though the number of elements is infinite, but that infinity is within our grasp or understanding. Okay. So for example, this set of natural numbers is infinite set, right? Okay. But can I say that infinite is in the set of natural numbers? I cannot say that. Okay, infinite is not a number. It's called NaN, not a number. You must have seen this error in computers and programming, not a number, NaN. So infinite is not a number, but infinite set is countable. Okay, so this is by definition. So my other question, set of rational numbers, which can be written as P over Q, such that Q is not equal to 0, and P and Q are set of natural numbers, for example. Okay, is Q countable? This is the question. Okay, and let's call it 1. Another question, number 2, set of real numbers. So is R countable? This is the question. So we will try to answer these 2 questions in the next class. And once we are able to answer these questions, then we will see that what is the structure of countability and how do we even prove something is countable or not countable. And once we have that idea, we will use that argument to prove why ATM is not decidable. Because the proof of ATM's undecidability depends on the proof of countability. Okay, and we will create the connection in the next class. So yes, any questions? Any questions before we end this class? No questions? Okay. In that case, thank you very much. Eid Mubarak to all of you. And I will see you Tuesday after Eid.
Hey, Mubarak, sir. Allah Hafiz.
Thank you very much.
हाँ थैंक यू सर प्रॉब्लम सर 2 अपलोड कब होगा
मैं कर दूंगा।
ओके थैंक यू सर ईद मुबारक
मुबारक।